Okay, so welcome to the second talk by Daria Pchelina. Sorry for the pronunciation. And so it will be about density of disk and Sphere packing. So the stage is yours.
Hi. So indeed, I will talk about the density of disk and sphere packings. So we'll start by a simple introduction to the topic, really simple. Then we will continue by talking about disk packings in 2D, and we'll conclude with sphere packings in 3D. All right, let's start. So imagine you are given an infinite number of identical copies of a coin, like this one. So how would you put it on an infinite table without overlap in a way to maximize the covered surface? So the configurations of coins posed on the table without overlap is called packings. Like here is an example of a packing. And you see that here the covered surface is not really large. We might make it more compact, like this. So who thinks that this configuration maximizes the covered surface? Now, you're clever. You're right, you got me. Okay, so this is the best way. I think you thought about this one. So this is called the hexagonal coin packing. And it is optimal. It's the best. It was proved a long time ago. Okay, so now I propose to you to generalize this problem. So now we have two possibilities. We can either consider packings by more coins, like 2, first of all, or consider sphere packings in more dimensions, higher dimensions. So the first step would be 2 coins and 1 orange in 3D. Okay, so when we consider packings by 2 coins, so we fix the pair of coins of given sizes, and then we are looking for the optimal packing by these coins. And so for some pairs of coins, the problem is solved. And so, for instance, for these 2 coins, the best packing is this one. It was proved. And the same for these 2, etc. For these 9 cases, it was solved, and for some others. So there are rather recent results.
Changing the relative size.
Yeah, so the difference here is that the largest yellow disk, we can always say it's unit disk, and the small one, well, it can vary between 0 and 1. So it's an infinite possibility for pairs of coins.
So what's the conclusion for any ratio of their relative? Any ratio we can find some optimal.
In theory we can, yes. It will always be reached on some packing, but it was found only for some cases, like for these 9 of them, and for some others. But many cases are without answer yet. We have some bounds, but
also we have some.
We have some bounds on the density, but not best candidates. Okay, so about oranges in 3D, well, the best packing is the one used in grocery stores for oranges. It's this one. So the idea is that we take 3 oranges and then we continue, well, with this one. And so actually it was called by Kepler a cannonball packing. He was militarist, Kepler. And he conjectured that this cannonball packing is what's optimal. And the conjecture remained open for 400 years. And it was finally proved in 2000 something. I will talk about this proof in the end of the talk because it's really interesting. Okay. All right. So both cases were solved. So now we would like to generalize even more. So we have several possibilities. We can consider packings in 2D by more disks, like 3, first of all, the first open problem. We can consider packings in even higher dimensions, like 8 and 24, which were solved. not long time ago, or we can both increase the number of objects, of spheres, and the dimension. So in this talk, we'll talk about ternary disk packings and binary sphere packings in 3D. We will not go any higher. It's too complicated. Okay, for ternary disk packings, I proved that for each of these triplets of disk sizes, each of these packings is optimal. So for instance, this packing is optimal among all packings by this triplet of disk sizes. But all of them are different. Okay, we'll talk about it later in detail. In 3D, as I mentioned, the cannonball packing is the best. And so now I propose to you to insert small blue spheres in holes of this packing, and like the largest blue spheres possible without overlap of the orange ones. It will be even denser. And actually, it turns out that this packing, it has the same structure as the crystal form of sodium chloride, known by chemists, and it's also called rock salt. So that's why we call this packing rock salt packing, and these are rock salt spheres. Many people think that this packing is optimal among all packings by rock salt spheres. And I didn't prove this conjecture yet. I hope to do it one day, but I make the first step towards it. Actually, I found a new upper density bound on packings by rock salt spheres. Okay, so we'll talk about these two results. I will just introduce you with the methods we use in our research. So actually, we start with purely geometric problem. So we need to use geometric tools. So first of all, for instance, we should study strange geometric objects like triangulations and simplicial partitions and everything, and geometric problems to solve these problems. We study also the functions which reflect the geometric properties of such objects, which are really, really complicated functions. So we use some tools to study these objects. For instance, we use differential geometry to study them. On the other hand, okay, our problems are nice, geometric, beautiful, and short. But nothing guarantees us that such kind of problems would have nice and beautiful solutions. And nothing guarantees us that they would have a solution, a proof at all. And moreover, actually nice and simple problems which still remain open tend to have complicated solutions. And by complicated, I mean in need of computer assistance. And so we need this computer assistance for various reasons. So some of them are just simply to perform symbolic computations, because again, we work with very strange functions reflecting some volumes, densities, and everything, which are really huge. And just to symbolically simplify them, we need computers. Another reason is that a packing is infinite. Space packing or plane packing is infinite. It's an infinite object. And actually, we cannot really work with infinite objects as a whole. So in our work, we reduce our problems into local ones. And so instead of studying an infinite packing, we'll rather study an infinite number of local cases, which might appear in this packing, like local configuration, like these ones. And actually, there is a huge, huge, huge number of such configurations to study. So we have to run through them by a computer. We cannot do it by hand. And the last reason is that we try to prove optimality of packings. So optimality usually means we try to prove some inequalities on some complicated functions. And moreover, as I mentioned, we actually prove these inequalities over an infinite and continuum sets of geometric objects. And so to do this, we use recursive subdivision and integral arithmetic, which are nicely implemented by a computer and cannot really be done by hand in the last case. Okay, so our problems are of interest for mathematicians, computer scientists, and actually also for chemists and physicists, more applied ones, those who are trying to create nanomaterials. So some of them, when they try to produce a new nanomaterial, what they do is that they take, like, for instance, two kinds of nanospheres and nanocylinders, and they try to mix them. And in the end, either they have a phase separation, that means that these particles do not mix well, so no new material is found, or they do mix well, like here, and they're happy because they have a new material. And well, in practice, what happens is that actually the sizes of spheres and cylinders, which have dense packings, like this one, they tend to mix well, but better than those who do not have dense packings. And actually, the result of this self-assembly tend to correspond to this dense packing in practice. So, like in these experiments, that's what happened. Okay, so the introduction is over. So we'll talk about these packings with precise definitions and more or less precise proofs. So if we're given a finite set of disks, a packing is a geometric configuration of copies of these disks on the plane without overlap. So here is an example of a packing on the plane. Okay, so we are interested in density of packings. So to define the density of a packing of the plane, we first define the density of a square, which is just the ratio of this square covered by disks. And then, taking the limit of densities of larger and larger squares, we obtain the density of the whole packing. And so our principal question is, given a set of disks, to find the maximal density which can be obtained by a packing by these disks. So, for instance, for this triplet of disks, this packing is optimal, has the maximum possible density. And usually we denote this maximal density by delta star. Okay, so now we're looking for optimal packings. And that's why we are interested in a class of triangulated packing. So a packing is called triangulated if each hole in this packing is formed by 3 pairwise tangent disks, like here. And we tend to think that these packings are good candidates to maximize the density because, well, they just look compact. And moreover, actually, locally around each disk, they are the best. Like everybody is tangent to everybody. It's really, really cool. So we'll start by finding these packings. And so, you know, the hexagonal disk packings for only one size of coin that we saw in the first slide, it is triangulated. So now if we consider binary disk packings, we have the large yellow disk of radius 1 and the small blue disk of radius r, which can vary from 0 to 1. So they are 9 values of r allowing triangulated packings. And so for each of these values of r, a triangulated packing is given here. Okay. Okay. So for ternary disk packings, we have 164 triplets of disk radii. Actually, I wanted to put it here in the beginning, but I cannot pick one. So I will put it this. well, you see half of it, but it's better than this one. So we have 164 pairs R and S, R being the radius of the blue medium disk, and S being the radius of the smallest red disk. And they're here, you can look at them later, allowing triangulated packings. Yeah. So it's a packing where the contact graph of disks, so the contact graph, we put an edge between these two, is a triangulation. So each hole is a triangle.
But if you only use one type of disk, then you are guaranteed with a triangular.
Yeah, so only one type of disk is the hexagonal packing, which is triangulated. And if we force ourselves to use the second one, then we have only these ones. And if we again force ourselves to use the third one, we have 164 radii here. Okay, actually, it was proved not so long time ago that if we fix the number of disks that we can use, there is always a finite number of disk radii allowing a triangulated packing. Yes?
For R and S, we have some combined. Okay, it's less than one, and
yeah. Actually, we always normalize here, so the largest disk is always of radius 1, and so R and S are between 0 and 1, and S is smaller than R.
And here it's theorems for arbitrary R and S.
Yeah, like that's all possible R and S that can produce a triangulated packing. Only 164. So this is a recent result. This one is kind of recent also. Okay, so for 4 sizes of these, there was an unpublished result. There are many of them, but they're not really interesting. Well, I want to notice that each packing here is periodic, and that means that it's a repetition of the same parallelogram. And so you can see the parallelogram actually here. So they can be repeated. Okay, so these packings, why we look at them, because they seem dense, they might be optimal. And actually it's the case. So the first one, the hexagonal packing, it is optimal, it was proved, it's cool. It turns out, it was proved not so long time ago, that for each of these pairs of disk radii, a triangulated packing in question that are shown here is optimal also. Okay, so it seems to be natural to assume that it would be the case for any number of disks, that systematically a triangulated saturated packing will be optimal if it exists. And that's the conjecture, we call it Connelly conjecture. So here I use the word saturated, which I shall define. So a packing is saturated if we cannot insert any more disks without overlapping the existing disks. So for instance, the first packing here is triangulated and saturated. We cannot fit any more disks in the holes. And the last packing here, it's not triangulated nor saturated because we can add a blue disk here, 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 everywhere. Actually, it's not saturated at all. And so from now on, we are only interested in saturated packing. We always assume our packing is saturated because actually inserting more disks in a packing doesn't decrease the density. And we are trying to find densest packings, right? Okay, so actually the first step towards this study of this conjecture is to look at ternary packings. And so with ternary packing, as I mentioned, we always say that the largest yellow disk is of unit radius, the medium blue one is of radius r, the smallest red one is of radius s, and there are 164 pairs rs allowing a triangulated packings. They are all here. We can actually depict them on a kind of a map. So here horizontally we have r, the radius of the blue disk, and vertically it's the ratio between S and R. So each point here corresponds to a triplet of disks allowing a triangulated packing. So for instance, here 36 you see that R is very small. So blue disks are really very small, and S over R is almost 1. So red disks are almost as big as blue ones. So you can see that it's triangulated packing. Indeed, it looks like it. So among these cases, there are some 15 gray cases, mostly here, which are not really interesting for us because no triangulated packing is saturated for them. So for instance, for this case, this is the triangulated packing, and we see that the red disk can be inserted here without problem, but it would not be triangulated anymore. So these cases are not interesting for us. And among the remaining cases, for 32 green ones of them, we proved that a triangulated packing is optimal. Like this one is optimal, this one is optimal also. And actually, we believed the conjecture to be true, and we were stuck with these 32 cases, and we didn't know what to do. And by chance, we found a counterexample. So actually, the conjecture is false. And we actually found even more counterexamples, 45 of them. And so for 45 red cases here, we found a non-triangulated packing, which is denser than any triangulated one. So the conjecture, which seems natural, is false.
Question.
Yeah.
I don't know if you said it already, but sorry for that. But how do you generate all these cases? I mean,
So this is the result of 2019. I can talk a bit later in detail, but basically what happens is when you have a triangulated packing, like this one, what you know is that for each disk of this packing, it has a corona, which is just the set of its closest neighbors, okay? So if you look at this corona, you know that, well, they're all triangles formed by 3 pairwise tangent disks. And you know that here in the center, the sum of the angles of these triangles will be equal to 2 pi. And so now to find all the values of R here, for instance, having a triangulated packing, we'll just run through all possible combinatorial sequences of coronas around each disk, like symbolically, like here we'll say, okay, I have R around the blue one, it would be 1 R 1 R, etc. And it's an infinite set of possible coronas, but actually we have the small disk cannot be too small, so finally it's a finite set because we cannot have too many disks around one of them. And so actually when we have the pair of coronas, so I say that around the largest disk I have this sequence, and around the smallest disk I have this sequence, it gives me some polynomial constraints of the value of R, because I have all these triangles whose angles can be written depending on R as a variable. And I know that all these angles should sum up to 2 pi. And so that gives me a pair of polynomials.
So then you are absolutely sure that you haven't missed a single case in the whole galaxy over there.
They are sure.
Sorry?
They are sure that they.
So there is a very robust and systematic way of constructing all possible cases.
Yeah. But for 4 disks, it becomes really long.
Yeah.
So. Yeah. But I didn't work on it. So. Okay. Questions? No? Okay. So we're here. So I told you what happened. So the conjecture is false, but we proved the optimality of some of these triangulated packings for ternary disk packings. And so now I will try to give you some ideas of the proof of optimality of such packings. Then we will talk a little bit about the counterexamples, these ones, and then we'll go to 3D. Yeah.
What do you mean with a binary non-random packing that are then only considering 2 out of 3?
Yes, actually we constructed our counterexamples using only 2 disks out of 3.
Okay.
Yeah. But any counterexample would do. Ours are really nice. Okay. So, as I mentioned, packings are infinite and really do not work with infinite stuff like this. So we try to localize our problem first, with the first step of our proof. And more precisely, we'll cut our packings into small pieces, which will be triangles of a triangulation. And so I will now construct the triangulation in question. We start by defining Voronoi cells of disks in a packing. So a Voronoi cell of a disk in a packing is just the set of all points of the plane closer to this disk than to any other. So here is the case of unary packing. Here is the case of a binary packing. So the partition of the plane into Voronoi cells of the disks is called the Voronoi partition of the Voronoi diagram. And our triangulation is just a dual of this Voronoi partition. So we call the triangulationist question an FM triangulation after its inventors, in the case of disk packings, Fegistott and Molnar. So now we have our triangulation. We shall define the density of a triangle of a packing. It's just the proportion of this triangle covered by disks. Okay, cool. So now we can cut our packing into small pieces. It's nice. And now I propose you to look at the sketch of the proof for the simplest possible case, the case of packings by identical disks that we already saw at the beginning. So here we have our hexagonal triangulated optimal packing of density delta star. And let's look at its triangulation. You can notice that it actually consists of identical triangles, like this one. We call it tight because it's constructed by 3 pairwise tangent disks. And so the density of the whole packing will be actually equal to the density of this triangle, delta star. And now it turns out that any triangle that might appear in some saturated packing is never denser than this tight triangle. So this guy is never denser than this one. This is kind of intuitive. It can be proved by a few lines of calculations, but we don't have time right now. You should believe me. It's true. And actually, it's the end of our proof, because we take any packing, and we know that for each triangle of this packing, its density is never greater than delta star. That means that the whole packing can never be denser than delta star. So now we've got our local proof, and local and geometric and really nice, for one disk packing. And now we would like to generalize it for our ternary case. So
You haven't proved that triangular packings are actually the maximum. You prove that these are maximal among triangular packings.
yeah, but any packing can be triangulated. So it's, and we all consider saturated packings. So yeah, so it's for everybody finally. So now I would like to invent the same kind of proof for multi-size disk packings. And now I have the first difference. We have several disk sizes, so we have several kind of triangles in our packing. And some of them are denser than others, and some of them, like this one, are denser than the density of the whole optimal packing, delta star. So we cannot find the same bound anymore. We cannot bound the density of any possible triangle by delta star. It doesn't work anymore. And so that's why we introduce the redistributed density. Actually, what we do in our proof is to define an alternative distributed density function delta prime, which will force these dense triangles to share their density with their empty neighbors. And so Actually, I will not show you the definition of delta prime because it's very complicated, but we constructed by definition in a way that around each vertex in any possible packing, our redistributed density is always less than the real density. Okay, and our proof, the remaining part of our proof, consists in proving that in any triangle, the redistributed density never exceeds delta star, like it was here with the real density. And so actually our proof now consists in proving this green inequality for each possible triangle. So it's still local, and delta prime is also local because it's defined locally around any vertex. And to obtain the same kind of a proof, actually, just we shall redistribute our density before doing the same thing. So now we'll try to prove this green inequality without even knowing the definition of delta prime. And so here we have a problem because we should prove an inequality on any possible triangle that might appear in any possible packing. And actually the set of such triangles is a continuous set, and it's of cardinality continuum. And our function delta prime it cannot be analyzed. I mean, we cannot do anything analytically. We should really do by brute force, by checking all the triangles by computer. And we have a problem because this set is clearly not finite, and computer, it likes finite things. So it turns out not to be that bad, because this set is continuous, but it's also compact. Actually, we have a uniform bound on the length of edges of a triangle that might appear in a saturated packing, because these cannot overlap, and so an edge can never be shorter than the sum of the radii in its extremities. Okay. On the other hand, we only work on saturated packings, so edges cannot be too long either, because otherwise we might insert a disk in the packing. So we have this uniform bound. So actually, each edge, the value of the length of each edge of each triangle is inside an interval. And now we can use interval arithmetic. So in interval arithmetic, each value is represented by an interval, and we can apply arithmetic operations or functions to intervals, and we're always guaranteed as a result to get an interval which will contain all possible applications of our function to all possible values of the initial interval. Okay, so now with interval arithmetic, which is nicely implemented by a computer, instead of proving an inequality over all possible triplets of edge lengths triangle, we will rather prove, so this is an infinite number of inequalities, we will rather prove one inequality of an interval which is defined as delta prime of a triangle whose edge lengths are intervals. So here we have an infinite number of inequalities. Here we have one inequality, but it's in interval arithmetic. And so actually the problem is solved because we can do it by computer. Interval arithmetic is nicely implemented, everything is cool. Except one thing is that we might lack the precision, because if these intervals are large, when we compute delta prime, the resulting interval might lack precision. It will not be a real interval which contains all values, it will be even bigger. And so we might have delta star inside this interval. And so in this case,
The third point, function define of this interval.
Yeah. So if delta star is inside this interval, we will subdivide, because that means that these initial intervals are too long And to augment the precision, we have to, well, we divide them by 2. And so if initially we have this box, which represents the triplet of the edge lengths of the triangle. So if delta star is inside the interval, we do not have enough precision. We'll subdivide each of the intervals by 2, and we'll verify this inequality on each of these sub-boxes. And if we still lack precision, we'll continue our subdivision again and again until we have enough precision to get this inequality for everybody. So actually, this works well. So if every triangle, its delta prime is less than delta star, the recursion will stop and we'll obtain our result, and it's what happens. Except one case. Actually, we can have a set of triangles satisfying the green inequality, but one of these triangles is the optimum, means that we get the equality on this triangle. And if we have at least one triangle like this, actually our subdivision will go again and again, or it will be in an infinite recursion, because when intervals we have always a little bit of non-precision, and actually we will never stop on this. So we should resolve this case. Well, it turns out that this happens only on a precise set of triangles called tide, formed by 3 pairwise tangent disks. And actually, by definition, we define delta prime in a way that it's in equality on these triangles. And so, to resolve the problem before, we take the epsilon neighborhood of each of these triangles, and we will resolve it separately. We will run the recursion on everything except this epsilon neighborhood. And in this epsilon neighborhood, we just prove that the tight triangle is a local optimum, just using by checking the partial derivatives around this tight triangle. And this we can do it with interval arithmetic, and this works. Okay.
Sorry,
yeah.
So is it? So I'm not sure I'm correct. So if that equation is satisfied,
Yeah.
then so the algorithm does not converge basically, because you cannot verify.
So if this equality is satisfied.
No, so in the previous slide, I mean.
Yeah.
So if delta prime is equal to delta star on some triangle,
yeah.
then
it will go forever.
So and that corresponds to having some optimal solution.
Yeah.
So how rare is to find so if you just start with like a random algorithm,
yeah,
so you just apply this algorithm,
yeah,
how rare does it happen that it is actually
an optimal solution? Actually, it never happens except these cases which we know in advance because we define them as optimal.
Okay.
In practice, actually in practice, either all triangles are strictly smaller,
okay,
or there is one which is strictly bigger because it cannot be the match. So
technically, you can always put yourself in a situation where this is never the case.
Yeah, if we isolate the cases we know in advance are equal, we just can run it and either it will be cool or we will find the false guy at some point. So actually, it always stops in practice. Yeah.
So the about 9, they have the same delta star.
Yeah.
That's a bit surprising because the translation is very different.
Yeah, but it's actually delta prime is the I shouldn't touch it. Delta prime is the function defined by hand, so it's a redistributed by density. So I define it like I want to define it, and actually in my triangulated optimal packings, all triangles are like this. So that's why each of these triangles gets delta star.
Yeah, let's see. The first one and the second one, how could they have the same delta? Or I misunderstood.
Yeah, they do not have just okay. So they all have different density. I define a redistributed density by hand. It's a function I define by hand, which doesn't really reflect the density. It's just I decided to redistribute the density in a way that all of them have the same delta prime.
Okay, but what's the definition of delta star?
A delta star is the optimal value of the density, it's the constant.
For the given three.
So the delta star is the density of this optimal packing.
Yeah, but then it should be between the two, right?
Yeah, so the delta is the real density. It's really the proportion of the triangle covered. And I introduced delta prime, which I do not give you. Just should believe me that I introduce it, and I introduce it in a way that on all these triangles it equals delta star.
All the other stuff by some definition.
And delta star is the optimal density. Yeah. Okay, so I moved many things under the carpet, so notably delta prime, but I don't have time, so sorry. Okay, so that was the end of the sketch of the proof, and it worked. That means that everything worked. The recursion stopped. All triangles were fine for the 16 cases. So each of these packing is optimal for the corresponding triplet of disk. And for other cases, which are a bit special. So here you can see that actually each of these cases is a mix between two binary triangulated packings. So for instance, in the first line, each of these packings is a mix between B8 here and something else. And so that means that the density of each of these packing is between the densities of this binary packing and this binary packing. And for all of them, B8 was the densest. So actually, we also proved that this packing, binary triangulated packing, is optimal for among all packings using these three disks, or these three disks, or these three, etc. And the same, this one is optimal among all packings using these three disks. So that means actually that sometimes adding a new disk that we can use if we want doesn't augment or doesn't increase the maximal density. So we do not use this disk here. We just use only two of them. Okay. So I don't have much time, but these are counterexamples. They are also inspired by binary disk packings. So actually, we noticed that if we take a binary triangulated packing like this one, and we apply a continuous transformation by inflating or deflating the small disk, and we try to keep as many tangencies as possible. It is transformation. So here we only break this tangency. Oops, pardon. Up. And here we only break this one. Okay. So when we do this, actually the density, it will decrease a little bit. Oops, but not much. So here we have 9.5 and here it's 9.39. Rather cool. Anyway, we notice this, it's called LIPN flow. And we also notice that for some of the ternary triangulated packings, actually the size of the smallest disk is rather close to the size of the smaller disk in one of the binary packings, like for instance this one. So we can apply this transformation by deflating the small disk until it matches the size of the small disk here. And up we get the density, which is higher than the density of any triangulated packing. And actually, it was the case for 45 ternary disk packings like this. So we just took two disks out of three. We assembled something which is even not triangulated, and it's denser than any triangulated packing using all these sizes. Okay, so these were the counterexamples. Let's go to 3D until we have time. So, as I mentioned, the densest packing in 3D is really.
20 minutes.
Ah, cool. Okay. That's cool. So I will remove this. So in 3D, the best packing is a cannonball packing, this one. And how we construct it? We actually superimpose layers of spheres posed in the hexagonal way. Okay, and we'll obtain the density p/3 square root of 2. And this packing is optimal. It was conjectured by Kepler, and this conjecture got a really long history. So the first advancement in this conjecture were made by Gauss, who proved that this cannonball packing is optimal among all lattice packings, which means packings where sphere centers form a lattice. But the general case remained open for a very long time. It even got to be present in the Hilbert's list of problems. So it was really important at the time. And so the person who resolved it was Hales. And the first sketch of the proof of the Kepler conjecture by him was published in 1992. So it was a sketch in the sense that all ideas were right, but there were some lemmas remained unproven. And so to finish this proof, he needed to collaborate with his student, Ferguson. And together they published 6 papers, really huge papers, accompanied by hundreds of thousands of lines of computer code. It was in 1998. And it was a proof. It was an enormous proof. So it took several years. It took a group of 13 referees to, actually they worked on it almost full time for several years to try to verify it. And in the end, they said to be 99% certain about correctness of the proof. So it was published.
Sorry, question. What was the code used for in that case?
Actually, there were many linear inequalities and many, actually the same stuff as I did, interval arithmetic and recursive subdivision and linear inequalities. So it was.
The proof was numerical or analytical?
Both. I mean, analytical 6 papers and numerical code. It was both. So it was published, the short version of 100 of pages only was published in the Annals of Mathematics, and the full version in BCG, which were, it is rather different from the first 6 preprints because
so
for
either a linear method or just a review of this method.
how
I mean, short version of this means a simpler method.
No. It was just a brief explanation with references to the real papers. No, it was just yeah. It was not a no. You cannot do it better than this, I think. So anyway, Hales was not satisfied with 99% certain, so he started the project of formal verification of the Kepler conjecture called spec for I don't remember, a sphere packing something. Yeah, and so this was a formal full computer proof with how it's called, proof assistance, several proof assistants. There was a huge group of many people. It was an international project, and after 10 years, they completed it. So it works, it exists. So the Kepler conjecture is formally proved. You can even download this proof and run it on your computer, and well, I hope you will be satisfied. So now it's full, it works. And so why I talk about it? Just to say that in 3D, for only one size of sphere, it's really hard as proof. For 3 disks in 2D, it was not that hard anyway. And so we decided to try it with 2 sizes of spheres because, well, well, first we hope to do it in a shorter amount of time and effort. And in the worst case, it will give us 6 papers, 6 publications. That's cool. Well, more seriously, we actually hope to use our methods from 2D on triangulated packings and apply it in 3D. So the first step is to find triangulated in 3D. It would be simplicial. So that means that the contact graph on my sphere packing should form a simple pure simplicial complex. That means that it consists of tetrahedra. And so actually for one side of sphere, there are no simplicial packings because the cannonball packing, this one is not simplicial. Okay. For two sides of spheres, Fermic actually proved that there is only one pair of spheres allowing a simplicial packing, which are rock-salt spheres I mentioned in the beginning. And so the simplicial packing question is the closed sphere packing, and all octahedral holes are filled with the small blue spheres of radius square root of 2 minus 1. So everybody thinks that this packing is optimal. And we didn't prove the conjecture, but we kind of worked on it a little bit. And so just to give you an idea of how we can proceed with the work, with the proof of this optimality of sphere or these packings, actually usually, well, we work with only local proof. We do not, it's only in 2 or 3 dimensions, it's not in higher dimensions where you can do things differently. Here we want to localize everything. So we'll prove things on local configurations. And so basically what we do is we take any packing, we say that, okay, any possible local configuration of any possible packing will never be denser than my packing or my perfect configuration. And so we start our proof by looking for configurations, local configurations, which might break this reasoning, which means local configurations which are really dense, denser than my packing or any local configuration in my packing. So they're really dense. But in practice, they cannot be prolonged. They cannot be continued to form something dense. So if you try to continue it, actually it's not dense at all. It's not dense as dense as this one. So we start by looking for these dense local configurations, which we call dangerous. And we started to do it for rock-salt spheres, and we found some of them that were rather predictable. So for instance, first one is the local icosahedron formed by spheres. And actually, this configuration has the densest possible Voronoi cell among all one sphere packings, local configurations. And it was called dodecahedral conjecture, which was solved. And so this is like the best possible guy formed by one spheres. And these two ones are inspired by dangerous configurations from the Hales proof of Kepler conjecture. Okay, so we didn't go really much further with our proof, but we decided to do something a bit simpler, like the first step to the proof of the conjecture. So this conjecture would be the tight upper bound of the maximal density. And we decided to give just another upper bound of the maximal density. So we decided to inspire ourselves with a 2-dimensional result by Florian, which gives a really nice upper bound of the density of binary disk packings. And he says, no packing by these 2 disks can be denser than the density inside this triangle formed by 1 large and 2 small disks. So the proof is predictable. What he does is he takes any packing, he triangulates it, and he says, okay, no triangle can be denser than this one. And so we decided to do the same thing in 3D. So first of all, in 2D, we have triangles. In 3D, we have our simplicial partition, which is defined kind of the same by Voronoi cells and duals. And so the analogous result to this one would be to find the densest tetrahedron, like for instance this one, which would be denser than any tetrahedron which might be present in a sphere packing. And so we almost done it. So our conjecture is the following, that each of these tetrahedra here is the densest possible among all tetrahedra formed by the same spheres. So the first ones are tight. It means that all spheres are pairwise tangent. And the 2 last ones are stretched. So the sphere here is tangent to 3 other spheres and the opposite phase. And so actually this conjecture, if it's true, it gives a new upper bound of the density on any packing, because actually what it gives is that no tetrahedron in a packing can be denser than this one, because it's a denser among these ones. And this would give us this upper bound. Well, we can continue even more. And actually the only upper bound of the density of rock-salt spheres was given by Daria et al. And it looks like this. So we can't really say if it's better or not, because it's really 3 points in his paper. But it looks better now. So we actually proved this conjecture for a subclass of star tetrahedra. So star tetrahedra are those where one sphere touches 3 other spheres. So basically all these tetrahedra are star tetrahedra. And so how we did it? Actually, we use the same exact method as for triangles in ternary disk packings. So around these optimal guys, we use the differential geometry to prove that they are local optima. And for everyone other, we used recursive subdivision and interval arithmetic with much larger formula than for disks, but it worked. And the fun fact, the space of all star tetrahedra is actually 3-dimensional, because we have one sphere which is tangent to 3 others, and so there are only 3 edges which are free. So as in this case, we have 8 recursive calls at each step. So why didn't we do the general case? So it's not proved, because for the space of all tetrahedra, we have 6 dimensions. So at each step, we would need 64 recursive calls, and it's too much. And so right now we're working on a geometric kind of a proof to remove the number of dimensions. So we're trying to contracting edges of tetrahedra and prove that the density doesn't decrease when we are doing this. And just a small remark, what does it mean too much? Well, 64 recursive calls is bad at each step, but it's not the real problem. The real problem is that when we have too many free variables in our formula, we are stuck, because in interval arithmetic, you can have a formula with each variable a really tiny interval. It's almost precise, actually. But since the formula is huge, the resulting interval will be enormous. We cannot work with it. So when I have 6 degrees of freedom, and we try to compute this at each step of our recursion, we actually will never converge, because we need to subdivide until almost infinity to get some reasonable precision. And for star tetrahedra, we fix 3 edges, and we fix the radii of disks. And so this formula becomes this, which are very nice and simple. And simple here means in terms of interval arithmetic. So here we try to minimize the number of occurrences of variables, because, well, it's the stuff of interval arithmetic. So I will stop here. Thank you for your attention.
Thank you for the very nice talk. And are there any questions?
Can you see a bit more about what is interval arithmetic?
So
as it is a typical application.
Uh,
Not no problem.
So actually in interval arithmetic, well, first it was introduced, it was introduced actually for precise computations, like computations with a certain precision. And so in interval arithmetic, each value you will represent it by an interval. And actually in practice, usually what we do is we work on real values, and we'll represent it by an interval representable in a computer memory. So for instance, a float with a certain precision. And so each value becomes such an interval. Like for instance, it was x, and we will denote the the extremities by x bar and x bar. And so now we can perform, for instance, an addition of two intervals. So for instance, if I have x and y, or y, sorry, and for instance, x is 0, 1, and y is 1, 2. So the resulting interval should contain all possible results on all possible pairs of these two intervals. So it depends on the implementation, but for addition, it will be simple. So it will probably be 1, 3. So x plus y. And it's an interval. We can also apply functions on intervals. Like, for instance, we can compute sinus of x, which, well, probably will be between 0 and sinus of 1, something, and other functions. And we can also compare intervals. So we can, for instance, try to compare x and 2. And so it will be true only if x is smaller than 2, all values of x are smaller than 2. And so it will be true in this case. But if 2 is inside x, it will be false. Okay. And so what we do in our research is we have a function is defined, well, for instance, for triangles, it was defined on a kind of a box of R. It was a box of the 3 edges of a triangle, because it's a space of triangles. And so now what we do is we say, okay, so I want to use integral arithmetic here. So what I will do is I will compute if f of the intervals x, y, and z, and this is the interval for this, etc. And so when I do this, I will obtain an interval which will contain all possible values of f on this box. Okay, but if the function is really, really complex, if it's not just multiplication, addition, etc., it's a complex formula, then this interval will be really large, and it actually will be bigger. Yeah, so here are the functions. Oh, there are formulas, actually. And what happens with integral arithmetic is that actually the resulting interval will depend on how the formula looks like. So if I give to my computer x minus x, and he isn't allowed to simplify it, and he should try to compute it in integral arithmetic, actually the resulting interval, it will be 0, minus 1, 1, probably. Yes, it will be minus 1, 1. But we know that this is the same variable. But in an implementation of integral arithmetic, he doesn't. And so that's a problem. Actually, it's not solved problem. We do not know. There is no algorithm which allows us to optimize the formula. So the resulting interval in integral arithmetic will be optimal, will be tight. And it depends on many factors. So we're trying to simplify it because we know that we do not want to see many variables, many occurrences of the same variable, etc. But it's not solved. And I am actually very interested in all results on integral arithmetic because I need it for my code to work.
Okay. Thank you. Another question? Okay. So let's thank Daria again.
Thank you.